A 6.0 earthquake just struck offshore Oregon and no, this isn't your typical rumble and move on kind of tremor. It hit at 3:17 a.m. local time, offshore and right on the doorstep of one of the most dangerous seismic zones on the planet, the Cascadia subduction zone. That name alone should raise eyebrows. It's the same tectonic boundary capable of producing magnitude 9 megaquakes and entire Pacific-wide tsunamis. And while this latest quake wasn't a monster, its timing and location are setting off alarms across multiple scientific fields: seismology, volcanology, tsunami research, you name it.
If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment. Your feedback helps shape what we cover next, and you being here keeps the conversation going. Thanks for watching. See you in the next one.
Let's be clear, a 6.0 isn't catastrophic on its own, but where it struck, that's what makes it a potential domino piece in a much larger, much scarier chain reaction. This wasn't just a one-off jolt. This was a tectonic nudge, one that might have just poked a sleeping giant. That giant is Axial Seamount, an active underwater volcano sitting about 480 kilometers off the Oregon coast. And it's not just any volcano. It's the most active submarine volcano in the entire Northeast Pacific. Scientists have been watching it closely for years as it quietly swells beneath the ocean. Seafloor monitoring has detected summit inflation. Literally, the volcano's summit is bulging upward from magma pressure. It's also been shaking with more frequent seismic tremors and showing every sign that something deeper is shifting. Now throw in that 6.0 quake. The two events didn't happen in isolation. In fact, they may be connected. Earthquakes in this region can alter stress fields for hundreds of kilometers. This one may have added just enough pressure, or released just the right amount of strain, to nudge Axial Seamount even closer to an eruption. And before anyone shrugs it off because it's just underwater, hold that thought. Yes, axial's eruptions are typically effusive, meaning they ooze lava rather than exploding. But don't let the lack of fireworks fool you. These eruptions can still trigger real consequences. Think earthquake swarms, seafloor collapse, and changes to the regional crust. There's historical precedent for this. It's not dramatic speculation, it's geologic reality. What makes this current situation even more intense is the timing. Over recent years, the signs have been building. More tremors, more magma movement, the summit bulging upward like a balloon. And now, we've got physical changes showing up along the Oregon coastline. Hairline fractures in cliffs are widening. Roadways are warping. There's measurable landward creep, entire sections of land shifting millimeters at a time. These aren't cosmetic issues. They're signs of systemic geomechanical strain. The entire coastal margin is under pressure, and it's starting to show. Then there's the ocean. After the quake, unusual patterns were reported. Irregular small swells, rapid breathing of the shoreline water moving in and out abnormally fast, short-lived harbor surges. Nothing massive, but definitely weird. Subtle but noticeable signs that something under the sea was disturbed. And in a region like Cascadia, weird ocean behavior is never something to ignore. That brings us to tsunamis. Everyone thinks of them as the product of one big vertical rupture along a fault line. That's true, but only part of the picture. There's growing recognition that tsunamis can also come from what scientists call secondary hazards. These include things like underwater landslides or volcanic slope collapses. And that's what makes this Oregon quake even more nerve-wracking. The slopes off the Oregon coast are steep, and they're packed with sediment. Shake them hard enough or shift them with magma movement and they can fail fast. That kind of submarine landslide can trigger a local tsunami with almost no warning. Not a distant event hours away, but something that hits in minutes. The usual early warning systems aren't designed to catch those in time. And here's where it all connects. Axial Seamount sits right on the Juan de Fuca Ridge, which is itself being shoved beneath the North American plate. It's a hyperactive geological zone. When magma pushes up at axial, it doesn't just make lava. It warps the surrounding crust. It shifts the stress across fault lines. It sets off tremors that could destabilize the very underwater slopes we just talked about. Scientists are well aware of all this. In response to the quake, they've already kicked monitoring into overdrive. Deep ocean pressure sensors have been recalibrated. Seismic arrays from Washington to Northern California are now running at peak sensitivity. Satellite systems are tracking land deformation from orbit. Even tsunami modeling software is being updated to account for potential new threat pathways. The public may not feel these changes, but the experts do. And what they're seeing isn't comforting. The coastal deformation, cracking cliffs, warped infrastructure is not just climate-driven erosion. The data suggests something deeper, accumulated strain that's building at an accelerating pace. GPS.
If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment. Your feedback helps shape what we cover next, and you being here keeps the conversation going. Thanks for watching. See you in the next one.
And INSAR data confirm it. The rate of movement is now beyond historical norms. That's not erosion. That's tectonic loading. It's the planet storing energy. And eventually, it's going to release it. But axial seamount isn't your typical volcano. It doesn't blow its top in dramatic, cinematic eruptions. It works in silence. The kind that reshapes the ocean floor without anyone noticing until a cluster of earthquakes hits or a harbor starts surging. The magma intrusion, the dike propagation, the swelling caldera, they all happen out of sight. But their impact is real, and they're often misread in real time. Seismic networks can't always tell whether a shake came from tectonic plates or a moving blob of magma. That confusion can delay warnings, muddy hazard assessments, and complicate emergency responses. It gets worse. Tsunami science itself is evolving. Researchers now understand that tsunamis don't always come from a single event. They can emerge from a chain of failures. An earthquake here, a slope failure there, a gas hydrate destabilization somewhere else. It's not one big splash, it's a series of cascading mini-crises that together unleash wave energy. And our current warning systems, they're not built for that kind of complexity. They're designed for the big one, not the domino effect. Fortunately, technology is starting to catch up. Underwater observatories like the Ocean Observatory's initiatives NOAA and Axial are now capable of minute-by-minute monitoring. They can detect the tiniest inflation of the seafloor. They can register microseismicity long before it becomes a threat. But there's still a gap between what scientists know and what emergency management systems are prepared to do. Real-time forecasting is becoming a possibility, but translating that into public action remains a challenge. And all of this sits atop one terrifying truth. The Cascadia subduction zone isn't dormant. It never was. It's alive, constantly shifting, storing energy, adjusting. Every small quake, every volcanic tremor, every seafloor bulge reconfigures the region's stress map. The quiet periods, they're not peaceful. They're pressure cookers. And the pressure is building. This latest quake might not be the event, but it's a reminder. A very loud, very shaky reminder that the Pacific Northwest is sitting on a loaded geological spring. The clock is ticking, we just don't know how close it is to midnight. Let's not wait until the water's at our doorstep. Stay informed, stay alert. If you live along the coast, keep an eye on updates from NOAA, USGS, and local emergency alerts. And if you found this breakdown helpful or at least slightly unsettling in a productive way, don't forget to hit like, share it with someone who still thinks the big one is a myth, and drop a comment with your thoughts. Are we paying enough attention to what's happening under our feet, or are we all just waiting for the ground to remind us? Subscribe if you want more clear, no-nonsense breakdowns of real events unfolding in real time, because the Earth doesn't care about your schedule. Let's get one thing straight, this wasn't some random blip in the seismic calendar. The 6.0 earthquake that just hit off the Oregon coast may go down in the books as moderate, but in this part of the world, there's no such thing as just another earthquake. Not here. Not where the Juan de Fuca plate is actively shoving its way beneath the North American plate like a slow-motion train wreck, and definitely not when one of the most volatile submarine volcanoes in the world is sitting right in the blast zone. Because here's what people often miss. Axial seamount isn't isolated. It's wired into the whole tectonic machine. It's a pressure valve, sure, but it's also a warning light. And right now, that light is blinking. Over the last decade, scientists have seen it swell literally. The summit has been inflating like something's pushing from below, because something is pushing from below. Magma. And not just a little. The pressure is increasing, the ground is shifting, and the frequency of those little tremors has been ticking upward like a countdown clock. Now combine that with the earthquake. A 6.0 might not flatten cities, but it does redistribute stress. That means crustal tension gets shuffled like a deck of cards. Some faults relieve pressure. Others, they get loaded even more. And when the stress shifts toward a volcano that's already swollen and twitchy, well, you don't need to be a geophysicist to see why that's a problem. Let's talk risk. Not the movie kind. The real kind. The kind that creeps in quietly through millimeter-scale land shifts and warped roadways. The kind you don't see until suddenly your cliffside crumbles or your harbor behaves like it's breathing. That's what Oregon is facing right now. Small signs adding up to something much bigger. And no, this isn't about fear-mongering. The scientists involved aren't waving red flags for fun. They're issuing carefully measured warnings based on decades of data. They're saying, pay attention, not because disaster is certain, but because systems are moving in a direction that could cascade fast. Because here's the wild card: submarine landslides. The continental shelf off Oregon is steep and packed with sediment. Under normal conditions, it's stable, but shake it up or disturb it with volcanic deformation and the whole thing can slump fast. And when that happens underwater, you get displacement. And when water gets displaced fast, you get a wave. Not a Hollywood-style monster wave, but something much more dangerous, a fast-arriving, near-shore tsunami. The kind that gives you 5 minutes of warning, maybe less. And these don't come from where you expect. Traditional tsunami alerts are calibrated for massive fault ruptures. They're good at detecting the big one, but not so great at catching a sudden slope collapse or a quiet volcanic flank giving way. That's why scientists are rethinking the entire model. Because real-world disaster scenarios aren't clean, they're messy. One event triggers another. And while the magnitude 6.0 earthquake might not have been catastrophic on its own, it could be the stress trigger that tips everything into motion. But the issue isn't just geological. It's also technological and institutional. Monitoring systems exist. They're good. In fact, they're better than ever. There are deep-sea pressure sensors, satellite-based deformation trackers, and real-time seismic networks. But they don't always talk to each other. The data's there, but integrating it, interpreting it, and turning it into public alerts, that's still lagging. And let's be honest, public attention spans are short. It takes a lot to get people to care about something like a seamount inflating 1,400 meters below sea level. But here's the catch: just because it's out of sight doesn't mean it's out of the picture. Axial seamount may lie far offshore, but its eruptions can ripple across the entire region's stress network. In fact, past eruptions have set off swarms of earthquakes, reshaped seafloor topography, and yes, affected the same fault lines that underpin the Oregon coastline. That's why every small shift matters. Every crack in the cliff, every road that buckles just a bit more than expected. These aren't random. They're symptoms. And they're telling us that the whole system is under strain. Even the ocean is acting weird. After the quake, harbor surges were recorded short, sharp, and unusual. They didn't flood towns, but they showed that the seafloor was moving in ways that displaced water. Shoreline breathing, the back-and-forth motion of the tide became erratic. Swells didn't behave normally. Again, not catastrophic, but strange enough that scientists took note. And when scientists take note after years of baseline monitoring, that means it's not business as usual. Which brings us to the Cascadia subduction zone, the heavyweight in this story. This isn't some obscure fault line, it's a megathrust, one of the most dangerous on Earth. The last time it ruptured fully, 1700, over 300 years ago. It generated a magnitude 9 quake and a tsunami that crossed the Pacific and hit Japan. And that wasn't even the worst-case scenario. The Cascadia zone stretches from Northern California to British Columbia. It's capable of storing centuries of energy and then releasing it all in minutes. The fact that it's been relatively quiet since the 1700s, that's not comforting. That's concerning, because it means we're overdue. The recent quake didn't rupture that fault, but it shook nearby terrain. It shuffled the stress deck. And the question is, what got loaded next? That's what scientists are trying to figure out right now. They're not saying run for the hills, but they are saying the system has shifted. The puzzle pieces have moved. That's why response teams are working around the clock. Seismic arrays are tuned to pick up the tiniest aftershocks. Deep-sea pressure sensors are watching for underwater slope changes. Satellite imaging is scanning for ground deformation along the coast. And tsunami models are being updated to account for multi-source threat paths, not just single-point ruptures. And still, there's a huge communication gap. Because here's the brutal truth. The most dangerous part of all this might not be the earthquake, or the volcano, or the underwater landslides. It might be the delay in translating scientific uncertainty into public understanding. Because geological risk doesn't come with a timer. It comes in probabilities, in maybes and if-thens. And that's hard to explain without sounding like you're crying wolf. So where does that leave us? With a region sitting on a geological tightrope. 1 foot wrong, 1 shift too far, and the system tips. Not necessarily into full-scale catastrophe, but into a complex cascade that's faster, messier, and more unpredictable than anyone would like. The quake was real. The volcano is active. The coastline is changing. And the science says, something is happening. We don't know exactly what comes next, but we know enough to say it's time to pay attention. So let's stop pretending that silence means safety. Because in Cascadia, quiet isn't peace. It's pressure. And pressure always finds a release. And here's the kicker, this isn't just a scientific issue. It's a human one. Because when we talk about the Cascadia subduction zone, or axial seamount swelling beneath the sea, or harbor surges after a moderate quake, what we're really talking about is whether the roads you drive on, the cliffs you walk by, the ports that fuel the regional economy, and the homes lining the coast are slowly, invisibly inching toward instability. We're talking about what happens when natural systems that have been quietly holding tension for centuries start shifting all at once. People want clarity. They want answers. But tectonics doesn't work on our timelines. It doesn't offer clean predictions. It offers signs, fractures in rock faces that weren't there a year ago. GPS readings showing millimeter-level creep inland. A volcano 1,400 meters below sea level sending out tremors that no one feels but every geologist notices. These aren't coincidences. They're cumulative. And while a 6.0 earthquake might seem small in a vacuum, nothing in this region exists in a vacuum. That's the whole point. The Cascadia margin is interconnected. A single tectonic pulse can send energy traveling hundreds of kilometers through faults, magma chambers, and submarine slopes like a shockwave through a web of dominoes. If that energy releases through a sudden axial seamount eruption, it won't look like a firework display. It'll be a rapid rearrangement of seafloor structure, maybe accompanied by a swarm of underwater quakes. If it happens near unstable slopes, it could set off sediment collapse. If it happens near fault boundaries, we might see stress loaded into the next vulnerable segment of the subduction zone. It's not that one quake will end the world. It's that each quake makes the system more likely to shift again. And yet, because there's no immediate catastrophe, the public reaction tends to be muted. Understandably so. People tune out the quiet stuff. But this is the kind of story that stays quiet until it isn't. The cracks in the cliffs, they're growing. The roads, warping more each month. The coastline, still shifting, slowly, and all of it points to a system that isn't at rest. It's resetting, readjusting, and those adjustments don't always end with a whimper. So what just happened off the coast of Oregon? It matters, not because it was the big one, but because it shows the system is moving. And every movement adds context, adds pressure, adds unpredictability. That's why staying informed isn't just smart, it's survival. If you want to keep up with this evolving situation, if you value fact-based updates without the fluff, and if you're tired of doom and gloom with no explanation, subscribe. Hit that like button if this helped break it down. Share it with someone who needs to know what's really going on beneath the surface. And let us know in the comments, are we taking these warnings seriously enough? Or are we still waiting for the ground to remind us the hard way? Thanks so much for watching. If you made it all the way to the end, you're officially part of the small percentage of people who don't just click away, and that means a lot. Before you go, I'd love to hear from you. Drop a comment below and tell me your thoughts, your ideas, or even what you'd like to see next. I read every single one of them, and your feedback genuinely shapes the direction of this channel. If you enjoyed the video, tap that like button. It tells YouTube this content is worth sharing. And if you haven't already, hit subscribe and turn on notifications so you don't miss the next upload. We've got more exciting videos coming, and trust me, you'll want to be here for them. This channel is just getting started, and your support helps it grow faster than you realize. Thank you again for spending a part of your day here with me. Stay curious, stay motivated, and as always, take care of yourself. Until next time, I'll see you in the next video.